So, hello everyone. My name is Ana Paula Mello. I work at Federal University of Santa Catarina in Brazil. Today, I will be the chair of the session 4, that is modeling and simulation studies. And the first paper Isha is going to present is ranking the thermal caliber of capacity building envelopes using data envelopment analysis. So Isha,
thank you.
Please.
I will just share my screen. Is it visible?
It's not in a full, yes, perfect.
Yes, okay. Okay. So, hello, I'm Isha Rathod. I'm a PhD scholar at Indian Institute of Technology, RoofKIT, and I'm going to present work titled Ranking the Thermal Caliber of Capacitive Building Envelopes Using Data Envelopment Analysis. So, this study presents a novel approach for efficiently ranking capacitive envelopes and using BEA. And capacitive envelopes include envelopes which have high thermal storage capacity, like concrete, stone, brick, masonry, etc. And in this work, I also talk about the concept of thermal caliber of capacitive building envelopes, which is based on the resistive and capacitive performance of the building envelope. And the study represents the inherent thermal storage capacity of building materials to rank their overall thermal performance, and it's used as a guide to facilitate the selection of materials by building designers and architects. Okay, so the building envelope is the building envelope acts as an interface between the outside and the inside, and both the components of both the aspects of resistance and capacitance of the material layers is impact the building performance. So high thermal mass materials are known to be effective for locations where the daily temperature difference is greater than 10 degrees centigrade, and an alternate phenomena of heat gain and heat loss occur at the building interface. And so the advantages of high thermal mass have been presented by previous studies by Balaras in 1996, Childs in 1997, and Yang and Lee in 2008. And these are basically in terms of reduced temperature fluctuations, reduced loads, and reduced need for cooling. And although previous researchers have also tried to quantify the thermal capacity of envelopes and to introduce them in thermal performance assessments, such as the dynamic benefit for the massive systems, which is DBMS, which describes envelopes performance in terms of the climate and material configuration. This was presented by Koseka and Kosney in 2002 and 2015 using US assemblies, building assemblies. The second study was mass enhanced R value, which is also used in the Building Code of Australia, which describes the R value, which describes the ratio of R value for massive constructions for the specific load compared to the R value in a specific location. And then thermal time constant TTC, which is a dynamic performance. Which represents the dynamic behavior of building envelopes, is also represents the response rate for a step change in temperature, which was also Sillingres extended the concept of thermal time constant into forward thermal time constant and reverse thermal time constant, which is FTTC and RTTC based on the distribution of thermal mass with respect to the wall's plane of symmetry. So forward thermal time constant represents the heat flow from outside to inside the envelope, and reverse time constant represents the flow of heat from inside to outside the envelope. Even though all these studies have been these studies have certain limitations, of course, and there still does not exist a unified framework to represent thermal capacity in building envelopes. So, yes. So in my work, I have performed this study for Ahmedabad, India. Ahmedabad, which is located in India and has a latitude of 23.04 degree north and 72.46 degree east. And this is classified as BSH, which is hot semi-arid steppe climate according to the Copenhagen climate classification. So in order to capture the present the seasonality in the weather data, a two-step clustering was done based on the daily maximum temperature, the daily minimum temperature, and global horizontal irradiance using the typical meteorological year ISHRE data. And so 4 clusters were obtained, and the clusters are fairly balanced, which as can be seen from these from the cluster sizes, and the different values for the considered parameters can be seen. Also, it is from previous studies, we know that thermal mass is not beneficial in colder climates. So clusters representing cooling dominant days are used for the study, which is cluster 1, 2, and 3, and cluster 4 is not used in the study. So in order to do this, in order to do the simulations, we needed a model. So a 9-meter square room was modeled, and it has 2 windows on 2 adjacent surfaces with a window wall ratio of 10%. And the window is 6 mm clear glass. The software used for modeling was ESPR. And the room is naturally ventilated. A fluid flow network was modeled to represent the airflow pattern based on the ambient air velocities. So a room node, a room flow node was considered, which was connected to the outside node to the fenestration components, to both of these fenestration components, and the ambient air velocity was used as the inflow of, as the inflowing air component. And windows are supposed to be open when the outside temperature is greater than 28 degrees centigrade, and otherwise they remained closed. So 4 scenarios were considered, which is basically single exposed scenarios. So for each simulation, only one facade was considered as exposed, and all the other surfaces were considered as adiabatic. The facade which was considered as exposed had a window. So, for example, this the figure on the right shows the configuration of the model for the south orientation. And the weather data considered was the ISHRE weather data, which is the Indian Society for Heating, Refrigerating, and Air Conditioning Engineers. And so this model was also validated using a residential apartment unit located in Ahmedabad. And the validated model, the simulation model, and the measured data were in agreement with an R-square value of 0.89. And so we considered a 300 mm wall, which is divided into 3 layers of 100 mm each. And each of these 3 layers can take up materials. So we also considered 3 materials, which were selected from the existing construction materials used in the Indian construction, in the Indian constructions of residential buildings. And these materials correspond to high and medium thermal mass materials. The properties of these materials are shown in the table. And so material A corresponds to a high thermal mass material, while material B and C correspond to medium thermal mass materials. So when we consider the envelope as 3 layers of 100 mm each, we get 27 possible cases because each of the layers can take up the 3 materials. So possible cases include AAA, AAB, AAC, and so on. So we have a total of 27 cases. So for these 27 cases, we get a thermal transmittance or the U value range of 1.76 watt per meter square Kelvin, and going up to 3.03 watt per meter square Kelvin, and the TTC range of 22.11 to 35.88 hours. And so data envelopment analysis, or DEA, is a non-parametric, non-statistical mathematical model which uses linear programming to measure the relative efficiency of decision-making units. So basically, decision-making units are the units which are considered for ranking, And what DEA does is basically assigns weight to each of the inputs and outputs. And the inputs and outputs are, of course, selected by us based on the criteria on which they are supposed to be ranked. And efficiency is defined for each DMU as the ratio of weighted outputs to weighted inputs. And the efficiency can lie between a range of 0 and 1. So 0 being least efficient and 1 being most efficient. So the thermal caliber for building envelopes is defined as the ratio of envelope performance, resistive and capacitive, on a particular day to its best performance in the year. So using DEA, we have this advantage of comparing the performance of a material on a given day to its performance in the year, and comparing the performance of an envelope on any day to the performance of other envelopes on other days. So in that sense, we can compare the performance of different envelopes on different days within each other. So it gives us a relative ranking for these envelopes. So in total, we have 7,560 DMUs, which are based on the 27 envelope cases we developed for each of the 280 cooling dominant days corresponding to cluster 1, 2, and 3. And we do it for 4 scenarios, which are the 4 exposure scenarios for orientations. And the inputs used are the FTTC and diurnal solar temperature gradient. So FTTC, or thermodynamic constant, represents the envelope properties, whereas the solar temperature gradient, which is the difference between the maximum solar and minimum solar, represents the ambient conditions. And the outputs considered are the daily total heat gain and the daily total heat storage. So daily total heat storage corresponds to the is actually the amount of heat which enters the inside spaces. And this is the quantity which we want to minimize for the cooling dominant day. And total heat storage is the amount of heat that the envelope can store in a given day. And this is the amount of heat that we want to maximize so that heat does not enter the inside spaces. So for solving the DA, I've used a software which is called Max DA Ultra version 8.7. And the model used a CRS, constant return to scale, output oriented, and undesirable output inseparable model. So CRS, or constant return to scale, is basically considers that the outputs increase proportionately to the inputs. That is, if the outputs are doubled, then the inputs are also doubled. Output oriented means that the outputs are maximized first before the inputs are minimized, because efficiency is the ratio of output to input, and output is in the numerator. So output needs to be maximized for the efficiency to be maximum, and inputs needs to be minimized for the efficiency to be maximum. And undesirable output inseparable model is used because total heat gain and total heat storage are contradictory outputs, which means that total heat gain needs to be minimized while total heat storage needs to be maximized. So what undesirable output model does, it considers the minimization of one output while simultaneously increasing the, while maximizing the other output. So total heat gain is minimized simultaneously as total heat storage is maximized. And because total heat gain and total heat storage are dependent on each other and the other two inputs, we use the inseparable model. So the methodology in a nutshell is basically clustering of weather data based on daily Tmax, Tmin, and global horizontal irradiance to get the cooling dominant clusters, and then modeling the thermodynamic model of the building for the 4 different exposure scenarios, and then simulating the developed model for the 27 envelope cases, which was developed based on the 3 layers corresponding to medium and high density materials, to get the outputs, which are then used in the data envelopment analysis to get the relative ranking of DMUs. So coming to results, so the results basically represent the 4 different exposure scenarios, and we can see this is basically a frequency distribution representation. So what we see is basically the efficiency of all these envelopes across the 280 cooling dominant days. So the first thing that we observe is that the efficiency of envelopes lie between 0.61 to 0.1. That is, the envelopes are efficient from 60% to 100% when compared amongst themselves. So And then we also notice that case 12 and case 26 have much better performance compared to other envelopes, case 12 and case 26. Now, both of these cases have a high U value, but they also have a high density layer. That is, they have material A in their composition. Also, we see that the south orientation and the east orientation perform much better than the west and north orientation because they have a higher number of the high efficiency days. So also the effective position of thermal mass is important when we consider the capacitive envelope. So for envelopes which have the same thermal transmittance, which is so because we made cases based on 3 materials, a lot of cases have the same U value. So for example, case 3 to 5, 3, 4, and 5 have the same thermal transmittance or U value. But we see that case 5 performs much better in comparison to case 3 and 4. And this is primarily because case 5 is has a higher external thermal mass composition. And this is because high thermal mass materials they absorb the heat entering the building, and they hold the heat and then release it back outside. But if the external layers are made up of a low thermal mass materials, it's going to the layer is going to saturate and will allow the heat to go inside. Also, when a high thermal mass layer is sandwiched between a medium mass layer, it performs better because again the middle layer will absorb heat and will hold it for some time before letting it inside. And this is contradictory to when a medium mass layer is sandwiched between 2 high mass materials and it performs poorly, as seen in cases. You can read more about these cases in the paper. Now, next we look at the pixel chart, which shows the performance of, which shows the efficiency of the envelope for the year. So on the x-axis we have the months of the year, and on the y-axis we have the days of the year. And each of the pixel or cells represents the efficiency based on the legend, and the pixels marked in gray are not considered because they either correspond to cluster 4 or Saturday does not exist. But so in this pixel chart, I have considered the south orientation or south exposure scenario for 3 cases which have the same U value, case 23, 24, and 26, which have a U value of 2.11 watt per meter square. And we see that case 26 performs much better than case 23 and 24 based on the number of higher frequency days. And we can also see this from the frequency distribution, case 23, 24, and 25. So, and
Isha, sorry, but I need to interrupt you because you are talking 20 minutes. We'll be only 10 minutes for each one. Can you go to the conclusion? I don't know, you can finish for sure.
Yes, so in conclusion, we have looked at the thermal storage capacity, which is often a neglected factor in building performance assessments. And building performance, being dynamic in nature, are influenced by layer configuration, material properties, and envelope orientations. And these are all considered in the thermal caliber calculations, which gives due respect to thermal resistance as well as thermal storage. So also, the efficiency of building envelope varies for different orientations, and it is not a constant value, but a dynamic value, as seen by the efficiency values throughout the year. And seasonal clusters can be utilized based on locations' seasonal criticality. So if the study is extended to other locations, you can focus on certain seasonal clusters which are more critical for that particular location for assessing the capacitive performance. Thank you. Sorry for extending the time.
Thank you, Isha. No, at least we have one less paper, so we could see a little bit more about your work. Congratulations for your presentation. Is there any question? Let me see here. No. I would like to ask you, Isha, just based on what did you set the window open for 28 degrees Celsius?
So it's based on the operative temperature conditions. And because we wanted, because at 28 degrees centigrade, the inside temperatures are going to be much higher because the room is naturally ventilated. So we want and because it will become like a hot box in a sense. So we want a much higher airflow to ventilate that here.
Inside. Okay. Thank you. Is there another question?
I think there's one.
Here.
No, I have not considered the reflectivity of the facade in this study because I'm primarily focusing on the capacity and resistance. But that is also one of the aspects which can be considered.
Perfect.
Yeah.
Thank you. Thank you, Gavin. And thank you, Isha. So let's go to the another presentation. Ashi, are you there?
Yeah, hello.
Yes. Hello. So the next presentation is development of reduced order thermal network models for indoor wall assemblies. So, Asha, you can present. Remember that we have 10 minutes each, and then we have 5 minutes for question.
Okay. Hello everyone, I'm Ashi Kansal, a PhD scholar from Indian Institute of Technology, Roorkee, India. Today I'll be talking about development of reduced order thermal network models for Indian wall assemblies. Energy simulations nowadays are being employed for real-time applications such as predictive maintenance, demand response, and urban scale energy management. Modeling and simulation of buildings can prove to be challenging because of increase in building complexity, which makes the whole process resource intensive and time consuming. So there is a need for simplified models which can predict the thermal performance of buildings. However, simplification of model leads to loss of data and accuracy. One promising solution is reduced order modeling, which is basically a simplified representation of large-scale buildings and complex geometry. It helps us in analyzing energy consumption and load profiles at a larger scale, such as city district scale. Prediction accuracy of reduced order models may vary based on the building type, geometry, and thermophysical property of the envelope. The study presents an application of reduced order models, particularly thermal network models, for a residential building considering 3 alternate wall assemblies. The objectives of the study are to develop a validated thermal network model of a building and evaluate its application for 3 different wall assemblies, to present the effect of model order reduction on the prediction accuracy. The study is limited to thermal network model of 3 widely used assemblies in India, which are aerated concrete, brick, and rubble masonry. The methodology adopted for the study is as follows. First, we did some real-time field measurements for a test bed located in Hyderabad. Then we developed an energy plus model of the test bed and validated using real-time data. Then we developed an RC network model of test bed and validated it using real-time data. Then we developed an RC network model of different orders and compared their prediction accuracy. Then we developed RC network model of the entire test bed for 3 different Indian wall assemblies. So what are reduced order models? Reduced order models are basically a simplified version of complex models. They require less input parameters and considers the effect of all the dominant parameters while neglecting all the others. This significantly decreases the time involved in solving the differential equations. They try to generate buildings having lower order but producing almost the same response, which reduces the time required for its evaluation. They can be used for real-time forecasting of energy consumption and demand. They try to simulate and adjust the thermal performance and load profiles of a building considering significantly lesser number of equations. They enable the user to perform such simulations with a reduced set of resources and consuming lesser computational time. Thermal networks or RC networks are a type of reduced order models which basically consider a building element such as wall, window, roof, etc. to be broken down into number of elements, assuming they have a uniform temperature throughout. The number of such elements is usually kept small so that the order can be reduced. Thermal network represents these elements using a series of resistors and capacitors. Figure 2 represents a thermal network diagram of a wall considering the wall has been broken down into two layers. R1 represents the resistance offered to the wall due to outside convection. C1 represents the thermal capacitance of the first layer of the wall. R2 represents the resistance offered due to conduction of the wall. C2 represents the thermal capacitance of the second layer of the wall. And R3 represents the resistance offered due to inside convection. The parameters of the thermal network model are usually calculated using material properties. It considers the thickness of the layer, layer's R value, area, layer density, and specific heat capacity of each layer. So coming to the development of thermal network model of residential testbed, this testbed is located in Hyderabad and is constructed using brick and RCC. Hyderabad predominantly has a tropical wet and dry climate, so we measured different environmental variables for the year 2020. We measured outdoor and indoor air temperature and we measured outdoor and indoor surface temperature. Figure 5 represents measured temperature for the month of July and December for a single week. Then what we did, we developed a detailed energy plus model for the residential test bed and took one room and tried to validate it by tuning the parameters. So it yielded a mean absolute error of 0.82 degrees Celsius. Then we tried to develop thermal network model of the bedroom. Basically a 3R2C model or a second order model was constructed. This represents the RC network model of the two exposed walls. This represents the RC network model of the roof. This represents the RC network model of the two windows, and this represents the RC network model of the two internal walls. Thermal network model of bedroom was developed in accordance to VDA 6007 standards. The value of resistors and capacitors was calculated using thermal properties of the materials used in the test bed. So what we did, we basically tried to use RC network to simulate the indoor air temperature of the bedroom. So we used a 3R2C model or a second order model and we compared the simulated RC network temperature and the measured temperature. So the model yielded a value of mean absolute error 0.76 degrees Celsius. An attempt was made to develop a thermal network model for the entire test bed for different Indian wall assemblies. So basically what we do is we try to construct an RC network model for the entire test bed to simulate the indoor mean temperature. We considered 3 wall assemblies and considered model of different orders which were 2C, 3C, 4C and 5C. Prediction accuracy of these different type of model orders were compared using one-way ANOVA tests. However, we found that there were no statistically significant differences between group means as determined by one-way ANOVA in case of aerated concrete. The results for brick and rubble masonry were also found to be similar. Then we developed a RC network model for the entire test bed considering aerated concrete wall assembly. For this we used a second order model, that is a 3R2C model. Then we tried to compare the thermal network model and the detailed model indoor air measurements. We saw that it yielded a mean absolute error of 0.61 degrees Celsius. From the graph we can see that the maximum temperature of thermal network model is corresponding to maximum temperature of detailed model. However, minimum temperatures, they are not corresponding, they are unequal. We also see that thermal network model, it estimates lesser heat loss when compared to detailed model. Then we try to develop thermal network model for the test bed considering brick wall assembly. Here also we used a 3R2C model or a second order model. Here we try to compare the indoor simulated temperature in case of detailed model and in case of RC network model. So when we compared, it yielded a mean absolute error of 0.638 degrees Celsius. From the graph we can see that the minimum temperature of the thermal network model is corresponding to the minimum temperature of detailed model. However, maximum temperatures, they are not corresponding, hence they are unequal. Also we can see that thermal network model, it estimates more heat gain when compared to detailed model. Now we try to develop a thermal network model considering the test bed to be made up of rubble masonry. Here also we used a second order model or a 3R2C model. We tried to compare the simulated indoor air temperature using thermal network model and detailed model. So we saw that it yielded a mean absolute error of 1.116 degrees Celsius. We can see from the graph that the maximum and minimum temperature in case of thermal network model and detailed model, they are not corresponding or they are not matching. Also, we can see that the thermal network model is estimating more heat gain and less heat loss when compared to detailed model. So finally, what we try to do is we try to compare mean absolute error obtained by considering different kind of boil assemblies. So we can see that as the U value and thermal mass increases, the mean absolute error also increases. So we can say that the thermal mass is associated with thermal capacitance. So some kind of correction factor needs to be developed for thermal capacitance in case of high thermal mass materials. So finally concluding the presentation, this study presented the thermal network model of three widely used Indian wall assemblies, which are aerated concrete, brick and rubble masonry. Thermal network model of the test bed was developed and validated, and it yielded a mean absolute error of 0.76 degrees Celsius. The mean absolute error of second order thermal network model for the three wall assemblies, it ranged between 0.61 to 0.116 degrees Celsius. The prediction accuracy of different orders was tested. No significant difference was found for the test bed under consideration. However, significant difference might occur with increase in building complexity and scale. The prediction accuracy of thermal network model increased with increase in U value. The prediction accuracy of thermal network model of low thermal mass materials was higher compared to higher thermal mass materials. Now further work is required to investigate composite wall assemblies and complex building geometries. Thank you.
Thank you. Perfect. Asha is present here. Yes. Is there any question regarding his work, her work? Let me open here, cash question and answer. Perfect. Thank you for your presentation, Ashi.
Thank you.
And let me ask you something. Did you use Energy Plus, didn't you?
Yeah, I used Energy Plus for the detailed model, and I used Open Modelica for the thermal network model.
Perfect. Have you tried to calculate the heat balance in Energy Plus with the you can calculate through conduction, but there is you can calculate heat balance through convection in Energy Plus. Maybe it helps you to understand the gain and loss through the elements from window for roof. So maybe it can help you to understand why sometimes you don't have why you have a difference from measure to calibrate, you know?
Yeah.
Yes. So just an option for you. Try to see the heat balance in the Energy Plus program that maybe help you to improve more your research.
Okay.
Okay.
Thank you. Thank you.
Is there any question? No? If there isn't, can we go to the next one? Yes, the next one is Nicholas. Is that? Are you there, Nicholas? Yes, perfect. Is Nicholas or Nicolas? I don't know.
Nicolas.
Nicolas. Perfect, Nicolas. So Nicolas is going to talk about RoofKIT, building simulation in sustainable housing at the Solar Decathlon Europe 2001-2002. So you can start, Nicolas.
Can you see it great?
Yes.
Good. So thanks for introduction. So yeah, my name is Nicolas Carbonare, and I was one of the tutors in our team RoofKIT, and this is the team from the Karlsruhe Institute of Technology that participated this year early at the Solar Decathlon Europe 2122. I'm really not sure if everyone is familiar with the competition, but it's an architecture and engineering competition for energy efficient and sustainable buildings. And it's called Decathlon because 10 contests are evaluated. And this contest range from energy, comfort, house functioning, architecture, affordability, urban mobility, and so on. And we decided to participate for the first time. And so in this competition, we have to propose a project, and our project, which is called the RoofKIT project, was the extension of an existing cafe in the Mirker district in the city of Wuppertal in Germany. We chose this construction situation because the competition itself took place in Wuppertal. In our project, we create a new living space with the historic building. So the building can be, the historic building is below here on the right side, and the new living space is on the upper side of the building. We decide to integrate solar energy in the whole building, both in the roof and the facade, together with an energetic upgrade of the existing building. We also propose the construction of a new ballroom, which is located between the apartments on the upper part and the old cafe, which forms a transition between the existing building and new structure. And we also pay a lot of attention to aesthetic integration as a tool to increase acceptance of new technologies in energy efficient buildings. But the competition was not only a design, it was also constructing the building for real in the solar campus. And of course, this building was huge and was not possible to be built. So what was built was a small corner and called the house demonstration unit. Here we can see how the small corner transforms first into a model, and on the right side, the real building that we built during the competition. I will just directly dive into the energy concept of the house demonstration unit. So the house demonstration unit combines passive measures for high indoor environmental quality and different technical solutions that yield carbon neutrality over the year. So our building consumes the same energy and generates, and this is around 60 kilowatt hour per square meter in year. We combine first a high quality thermal insulation and ventilation with heat recovery systems to minimize energy losses in the building. Then we gain energy from the sun in form of PVT collectors, which provide heat, water, and electricity at the same time. The electricity is used by the building, and we have an energy management system that maximizes the self-consumption of this generated solar energy. And the hot water of the PVT system feeds a heat pump, which creates hot water as well for floor heating and domestic hot water consumption. And one tiny little part of our work was to prove how this concept works in simulation. So our team of engineers and architects decided to perform a rather deep system simulation. We decided to do the simulations using Modelica, as it is an equation-based language. And this is rather easy for people who are not experts in in building simulation, as you write equations and not deep code. The other advantage of using Modelica is the huge open source community. We took advantage of different open source libraries developed by different research institutions. And these models were developed with 2 seminars in the lectures in the Faculty of Architecture at KIT and in collaboration with the University of Applied Sciences in Offenburg. So again, this whole simulation study had educational purposes. I will not get very deep into the Modelica models, but they are available on GitHub freely. So the main model, just a short summary, the building model follows the very popular ISO 13790, where we fit a model using 5 resistances and 1 capacity to represent the whole thermal mass of the building. We modeled the heat pump using the characteristic curve based only in the inlet source, heat source and heat sink temperatures, and not in the mass flow. For the PVT collector model, we use separate models for the electrical photovoltaic panel and the thermal part of the PVT. And for the thermal output, we use direct and diffuse solar radiation, as well as first and second order losses and capacity losses of the collector. So going shortly to the results, we can see here on the left side the energy balance of the building. And we can see we only require space heating considerably in 5 months over the year. October is just a little bit. And we can see on the right side the electrical energy balance of the building. So the orange part is the consumption of the heat pump, both for hot water and space heating. In gray is the house consumption, which is rather constant in every month in the building. And in green is the PV generation, which of course has the highest values in summer. And this is the balance that we can confirm that the house generates in the whole year the same amount of energy as it consumes. So taking a sample day to see how our systems react, we can see on the left side the electrical power balance of a single day. This was in fall, I guess. Yeah, in fall, because we have some space heating. We can see the orange curve, which is the house consumption of the energy. The blue curve is the power that is provided by the battery. So when it's positive, the battery is being loaded. When it's negative, the battery is giving energy to our house. And in green, again, the PV generation, energy generation, and in gray, the energy consumed by the heat pump. And we can see more detail on the right side that, of course, every day in the morning, the heat pump produces with a lot of spikes due to our self-developed control strategy. They produce hot water with very high COPs between 5 and 6, which matches the manufacturer details of the heat pump we use. For space heating, we have a COP around 4, but in general, the COP levels are very high as we use the PVT as the heat source for the heat pump. And I just wanted to show shortly our results in indoor comfort and room temperature. We can see on the left side the adaptive comfort model, and we can observe as well that we are around 95% of the time between the first 2 comfort zones. And what was important for us on the right side was to show the comparison between measured and simulated indoor temperatures, because it was the only variable that we could compare directly between simulation and measurement during the competition. And we can see that our developed building model matches pretty well the measurements provided, the measurements that we carried out during 3 days last summer. So in conclusion, we developed a building and system simulation framework for the educational context. We use these simulations for students from different backgrounds and professionals, that they work together to achieve an overall concept, which was useful for us to take decisions in different levels. And that leads us to the second conclusion, that we use building simulation as our main decision-making tool in a real building design. This was used for building envelope, night ventilation, the control strategies for HVAC systems, and so on. So this was just a simple part of the whole simulation work during the team. And I want to thank you all for your attention, but also mention so we are glad that we could win the competition, and our building simulation efforts were really high considered by the jury during the whole competition. So if you want to take a look at our website, our Instagram, or our building simulations models, they're all freely available on the internet. And I hope this is also extendable to other educational purposes. Thank you.
Thank you, Nicolas, for your presentation. And I would like to congratulate you and your group for sure for using Modelica. It's not so easy. We need a lot of to know a lot of programs and how to build the scripts and stuff like that. Yes. And in 2019, we also participate from our group here in Brazil from Solar Decathlon in Latin America, was in Colombia, and was really difficult as well, but we also won the first one and the first place. But as you said, you should build your house. So it's really difficult because first you need to simulate, to understand, to study, to design all the stuffs, and then you go in local and you build everything, and it's really hard. So I'd like you to, if you can, just tell us about some which was the most difficult part in the whole process, in your opinion.
Well, there were a lot of difficult parts, as you said. Building the house is a challenge. It's not really easy. So it's the student competition, you know, and everything is nice on paper. So this design challenge, we designed this huge building with the extension. It's all just renders and drawings and calculations, but we had to build the self-demonstration unit. And making everything work was also very challenging. So just tuning the heat pumps, the ventilation systems, the oven, or just having electricity on the house. We are all students. That's also very challenging. And
yes,
I mean, the team for us, it was mostly composed by architects. And our engineering group was rather small, but I guess with the help of a couple of professionals, we managed. And the last graph I showed, I think it was one of the things we are most proud of, that we could really show that building simulation works, because we measured the temperature, we placed a heat source this was turned on every 4 hours over 3 days, and nobody could get in or out. So for example, all the shading systems were down and all the windows were closed, so the boundary conditions were known. And we had to use our model to represent that, and our model worked really well. And
it was kind of a calibration, yes?
Exactly, but
yes.
we didn't calibrate, we just used the data that we were like the theoretical data. And so it means what we built made sense in the simulation. It's something we could prove after building the building, but
yes,
it was also very nice to see.
Yes, perfect. Congrats. I know that's
Thanks.
really hard. Congrats. Perfect. Is there another question for Nicolas? No? Can we move to the last one, but not the least? Yes? So thank you again, Nicolas. And the next one is Sanobe. Are you there? Yes?
Yes, I'm here.
Hi.
Good evening, everyone.
Hi, nice to see you. So Sanobe is going to present about performance evaluation of phase change materials for cooling photovoltaics and enhancing efficiency. So please, can you present?
Yes, can you see my screen?
Yes, I can. It's not on full mode, but I can. Yes, perfect.
Right, so let me begin. So this presentation is on the performance evaluation of phase change materials within the global south locations. And it's not just me, it's I've got Shivangi and Silyang as well, who did work on this paper, especially Shivangi with the experimental work. So the motivation for this study was that we know that photovoltaics efficiency, it declines as the surface temperature heats up in hot climates. And there are different methods to regulate for the thermal management of PVs. And one of the methods that could possibly be used is phase change materials. But the problem with PCMs is that they're a double-edged sword, which can be seen from this experimental data set over here. So this is the experiment conducted by Shivangi, which has CPV, an integrated PCM on the back side, on the bottom side. And it was exposed to different doses of solar radiation, and the efficiency data recorded. And we can see that the PV average surface temperature has quite a strong linear correlation with efficiency for the two kinds of panels, with and without PCM. The blue one is without the PCM, while the orange one is with the PCM. So this was the data that was acquired in the experiments, and we thought, could we possibly use a typical building energy modeling tool to assess this performance at different weather conditions. So that's where the research gaps came up with. So there was limited work on PCM integrated PV modeling and simulations. Generally, even the work that was done, it considered limited geographical locations with very few studies in the global south. Most studies that employed simulation approaches did not use the typical building energy modeling platforms, such as Design Builder, Energy Plus, or similar. So we saw that there was a gap to develop a methodology that incorporates these BEM tools and test PCM integrated PVs across multiple locations. So that was the kind of gap we identified to develop this methodology. So this was what was developed. It's basically a co-simulation approach, but before this was done, from the Energy Plus weather data, a total of 885 global south locations were identified. The weather files were downloaded and then filtered based on these two criteria, which were that the peak summer temperature should be in excess of 25 degrees centigrade, because if it's not hot enough, then there is no point in trying to use the PCMs, because PV efficiency drops at hot temperatures. And then the second condition was that the monthly average swing should be at least 10 degrees centigrade, the monthly average diurnal swing. So that was to allow for making the assumption that PCMs would be charged and fully discharged over a cycle of a day. So with this filtration of the weather data, we identified 128 locations, which were then simulated using the co-simulation approach managed by MATLAB. So MATLAB managed the BCVTB, which is an interface which connects Energy Plus to MATLAB for any kind of simulation work that is not available already in Energy Plus. So this was implemented, and how it was different from a typical co-simulation was that it is set up in a way that you could simulate for multiple weather locations or multiple building types by editing the XML, the BCVTV XML in this iterative way. And within each time step, the PV surface temperature was calculated by Energy Plus, which is then used to read the efficiency data from the experiments and then read back into Energy Plus for further simulation time steps. So this approach basically allowed us to simulate the performance of the PCM for multiple locations or multiple buildings if need be. The building was not the focus in this study, so just a reference building was used, but the point was that this methodology incorporates typical BEM tools such as Energy Plus. The results, they look something like this. This is for the case without the PCMs. And so this is to set the baseline. From the experimental data without the PCM, this is what it looked like for all the locations. And we can see that the median efficiency of the PCM, the median annual average efficiency ranges from around 9% to 11%. And that was consistent with the lab experiments as well. So this was done without the PCM and then with the PCM to see what is the difference in the efficiencies. And this was plotted in this graph over here. I'm going to just change this to a laser pointer. So we can see over here the x-axis has the 128 locations. The y-axis is the absolute change in PV panel efficiency. So if we have a 0.4 improvement, it is something like if the baseline was 10% efficiency, then the improved would be 10.4. So this is an absolute improvement. So we can see even from this figure that more of the points lie towards the negative side. But these points are also color coded based on the average annual PV surface temperature for the case without the PCMs. So if there was no PCMs incorporated, the brighter colors tell us that there were more hotter climates. And you can see there's a visual trend that for these higher temperatures, PCMs efficiency improvement because of the PCMs, it is occurring. But how much is it? It is relatively from 2 to 7%, and it occurred over 36 locations. So for the locations which have a positive improvement, that is 36 out of the 128. For the colder climates, we see that the efficiency reduced. The worst case is location number 52, which was Dong Ujimquin in China. And in that specific case, the efficiency reduced from 11.41 to 10.88 on an annual average. And that's evident because if it's generally a colder location, then even the experimental curves, we see that there is this threshold in surface temperature, which only after that threshold, we have an improvement in efficiency with PCM. For the best case scenario was a hotter location in India, Hisar, location 109 on the x-axis, and the efficiency went from 9.26 to 9.92. So that was the best case, but we can see that there's just one data point over here. Most of them lied between 0.2 and 0.4% absolute improvement. So this kind of tells us what the analysis reveals for the multiple locations. But let us look at the best and the worst case scenario to understand a little bit more. So this is the best location where it was Hisar, India. And we can see on the right-hand side, this is data from several days in April, and only daytime data, obviously, because that's when we have sunlight. And the blue trace is without the PCM, and the orange trace is with the PCM. And we can see that the orange trace has smaller fluctuations in the PV efficiency, and that is what is acceptable and sensible, because the PCM, its efficiency improves when it's peak summer, peak afternoon. So we can see that that it doesn't drop, the orange trace doesn't drop as much as the blue one. But in the early dawn or maybe late eve, just when the sun is about to set, the PCM actually does not what we need. It reduces the efficiency. The orange trace is lower. So we see actually the smaller amplitude of this orange curve, orange trace, and that's what we would expect with the PCM. It's also reflected in the annual histogram on the left side, which kind of tells us that with the PCM, the data is more compressed, lower standard deviation, and a slightly better improved mean as well. So it tells us that it is giving us more consistent performance. As compared to the worst location where it's simply the amplitude is still smaller, because that's what the PCM we expect it to do, but also it's just simply lower than the case without PCM, because it is making it warmer. And we can see that reflected in the annual histogram as well on the left. So what are the conclusions? So of the total of 885 locations based on this methodology, 36 were identified which could have some potential of employing PCMs for improving the efficiency of PVs. Then we saw that the reason where it was giving that improvement was because of more consistent performance, lesser fluctuations in efficiency as compared to without the PCM case. And that this study employed an automated core simulation approach, which means that you can set up several buildings and multiple locations and press play, and it will generate all those simulations and results. By incorporating the experimental data, coupling the experimental data of the PCMs with that of building simulation. So that was a key objective. So there's the limit. Are there limitations to this work? Yes. It was based on one experimental data set, one PV-PCM combination. So that's the results may change for different PCM product or a PV product or a combination. Then inclination was not investigated. However, it should be easily done because it's simply of the case of changing the inclination of the roof on which the PV would be employed in Energy Plus, so that could be easily done, but it wasn't done here. Then it could be extended to a larger set of locations. The electricity generation could be compared in addition to the efficiency, because if we have a balance of efficiency, the loss and gains, they balance each other out. For example, the gains in efficiency in the afternoon, if they balance the loss of efficiency in the early morning, then in efficiency terms, they would cancel out, but not necessarily in electricity generation, because there may be more sunshine in the afternoon. So the results might be slightly different for electricity generation. And then this approach, we had a constraint of considering locations with sufficient diurnal swing. That was because we didn't actually model the physics of the PCM. We coupled the experimental data to the building model. So that's what we did. And that is all. Thank you very much. Any questions?
Thank you, Sanobe, for your presentation. It's not easy to work with PCM, yes? And I would like to ask you, but you already mentioned in the limitations about the inclination. Yes, it's something that maybe can improve, yes? Because it can vary.
It could be easily done because we just took a reference building from the DOE website, and it has a flat roof in this example, but to consider different variations, we just need to have buildings with different inclination angles, and again, we can assess it parametrically with the same simulation approach. So that's the reason for developing this methodology, because it integrates well into that building energy modeling process. So inclination, things like this can be, yes, easily done. And it's actually, we will do this. This is one of the comments we got for this paper. So we will do this and check the effect of inclination for those locations as well.
Yes, just to see how much it affects the results, yes. And did you model the PCM in the Energy Plus program?
No, so we did not, and it's so Energy Plus doesn't allow us to couple PCMs with PV. That functionality is not there. So we thought that by coupling the experimental data to Energy Plus, we can actually see if it would be worth doing. So in this case, we've got 36 locations out of 885, and we could have these gains. So if a more extensive exercise is carried out and we find that, okay, yep, this is worth modeling the physics of PCMs with the PV in Energy Plus, we need to integrate that physics into the platform, then that effort would be warranted. But with this exercise, at least we can assess if we need to do that or not, or if it would be just a time-wasting exercise because PCMs don't offer much benefit for thermal regulation of PVs.
Yes, and did you use only one PCM, yes? One type of PCM?
One type of PCMs for several different radiation doses. Yeah. It was concentrated PV. So that's actually that work was done by my colleague Shivangi. So yeah, the experimental setup is detailed in the paper itself.
Perfect. because we are trying to use here, not in PV, but in walls and roofs,
Yeah.
2 different types of PCM. Yes, to understand how they work and how can improve the stuff that we desire for. For example, maybe 2 different kinds of PCM can improve something that you're doing.
Yeah.
Yes?
So this is just the case of coupling experimental data. So if you've got different kinds of PCM, you've got enough data for that, which has a reliable fit, then you can just use the same approach.
Yes, perfect. Thank you. Thank you for your presentation. Is there any question? Shivanji is here. Yes.
So if anybody has question about the experiment, then we've got an expert on that to answer.
Everybody's quiet. No questions today? Okay, but don't forget you can download the abstract and the full paper in the website. So if you'd like to contact someone that presented today, the contact is over there. So I think I will end the session. Yes. Yes, we do have a break. Thank you, Alan. So thank you, Isha. Thank you, Ashi, Nicolas, and Sanober for the presentation. It was a pleasure to be here and to meet you today.